Okay, this is your start of the notes on a couple of things. For this video, we're going to be looking at the graph of y equals e to the x and the graph of y equals natural log of x. And you can go ahead and title your notes and fill in the appropriate notes number, and then we'll be ready to start. So the first thing that I want to remind you about is that there is a special number that we call e, just like we have a special number we call pi and a special number we call I. And what I've done is linked a video for you. It's called a Numberphile video. Numberphile has a whole bunch of really interesting math videos. So you'll see down here there's a note. There's a Numberphile video on the number e. It's about 10 minutes. I want you to watch that and you can learn more about the number e, where it came from, and so on. And just to summarize, E is known as Euler's constant or Euler's number. Here we have Leonhard Euler, looking pretty spiffy. You don't say Euler, you say Euler. And it's known as the natural base as well. E comes up in a lot of examples of, say, population growth or radioactive decay. Lots of things that have to do with growth or decay. Heating and cooling, all kinds of things. And e is irrational, so you can't write it as a fraction. As a decimal, it goes on and on and on, infinitely far without repeating. But the approximate value of e would be really good for you to know. It's approximately 2.718. Just like you know the approximate value of pi is about 3.14. Okay, remember from our last lesson when we were looking at the graph of exponential growth and decay. So here I'm looking at the graph of y equals a to the x, where a is greater than 1. That would be exponential growth. The base is greater than 1. So that would be something like y equals 2 to the x, y equals 3 to the x, and so on. Well, if e is approximately 2.718, that base is greater than 1, and so that graph will look just like our other exponential growth graphs. I mean, maybe more or less steep. Compared to 2 to the x, it would be more steep. Compared to 3 to the x, it would be less steep. But you have the same general shape. You have the same y-intercept here at 1. The domain, all real numbers, just like it was for all the other exponential growth functions. The range, y is greater than 0, just like it was for all the other exponential growth functions. And the asymptote, the line that the graph gets infinitely close to, the further and further out we go, that is also the same, y equals 0. And if you want to get a little bit more specific when graphing and you're trying to find a few exact ordered pairs, then you could just plug in different values for x like we typically do. So we would have e to the negative second, e to the negative first, e to the 0, and of course that's going to be 1, e to the first, e to the second, and so on. Those would be the exact coordinates. However, for graphing, it would be very helpful to know the approximate values. So if you grab your calculator, you need to know where is e on your calculator so that you can work with it. So you have two choices for where to find e. Notice that right down here, there's a button that says ln, that's natural log, right next to the 4, and above it, the second function of it, it says e to the x. So I would press second, and then that will take you to the e to the x if you press the natural log button. And that's assuming that you're going to be raising it to a power, because most of the time when you're using e, you will be raising it to a power. So e to the negative second, we get that number. We could approximate it for graphing. Again, if you needed e to the negative first, and so on. And there's a second place you can find e. If you look at your divide button, the second function of divide is also e. That's just regular e. So I could press second divide, and that gives me an e. If all I want is e, I can press enter. There's the approximate value of e. Or if I want to raise it to a power, second divide gives me e, and then the button right above it is the raise to a power button, and then you can put whatever exponent in there you want. Okay, so back to the table of values. Okay, so we get approximate values for these numbers about 0.14. My equals with a dot means approximate. About 0.37. E to the first is about 2.718. And e to the second is about 7.39. You could use those for more accurate graphing. Okay, of course, we also want to look at the inverse function, and we know that the inverse of exponential growth is logarithmic growth, and we know that that looks something like so from what we've done before, where you have an x-intercept at 1. And I just want to remind you that when you see ln of x, it means log base e of x. It's just a special symbol for the natural log. Ln means natural log base e. Notice I have parentheses around my x over here. I didn't put parentheses around my x over here. It's really not necessary to have those parentheses. Sometimes you'll see them and sometimes you won't. Okay, since e is a base that's greater than 1, the graph of y equals natural log x should look like the graph of any other logarithmic growth graph with an x-intercept of 1, with a domain of x is greater than 0, a range of all real numbers, and an asymptote of x equals 0. And of course, if you want some exact ordered pairs to plot, just like we've done in the past, what I would recommend for a logarithmic graph is instead of picking your x values and finding their y's, pick your y values and find their x's. Now, we haven't talked a lot about logarithms yet, reviewing how they work, so this could be difficult right now. Another thing you could do is just grab a calculator and plug in some different values of x and get approximate points. But we do know that for inverses, whatever ordered pairs we had for y equals e to the x, we will switch those x and y coordinates and we'll get the ordered pairs for the inverse. So that's what I'm going to do. Just switching the order of the x and the y coordinates on the ordered pairs we had on the previous graphs. And we already had those approximate values. Those could be plotted to give us a more precise graph. So that's just a reminder of what e and natural log, how they play into these exponential and logarithmic functions.